Hello everyone. So I'm Amine Kerkeni, GDE in machine learning from Tunisia, and I work at a startup called InstaDeep, specialized in artificial intelligence. And today we will talk about profiling machine learning models. So, but before starting talking about profiling, why do we need profiling? We usually teach you machine learning by showing you how to design models to write code, but we rarely teach you how to fix problems when your machine learning model doesn't work. And during the lifetime of machine learning project, you will usually encounter a lot of problems that can come from different pieces of your system. We can cite from these problems, problems coming from bad data. For example, you don't have the right data fed to your machine learning model because you're using the wrong folder, or you're using, for example, the test images instead of training images. You are not using the right labels and things like that. You can have also problems coming from bugs in the pre-processing. For example, if you do data augmentation, your data augmentation pipeline can be bloated and you have a bug somewhere. You can have a normalization problem. For example, you're thinking that you're passing values between 0 and 1, and in fact you're passing values that are not normalized. You can be using the wrong loss that is not adapted to your machine learning model or problem. You can have everything okay, but your neural network is too small or too big, so it doesn't learn much. You can have imbalance in your data. You can have an architecture that is not fit for your problem. For example, you have time series and you're using dense network, so you're not really leveraging the dependency between your data points. You can have leaks in your data. You can have wrong or inappropriate hyperparameters. So the problems can be coming from everywhere. You can also have slow training pipeline. So instead of training your model in a few minutes or a few hours, you need to spend days or weeks to get results and things like that. And the complexity of machine learning model is always growing because the trend in the industry is to use bigger and bigger model and more complex models. But what are our options to identify our problems and to help us avoid what you see in this comic? Just stir the pile until they start looking right. So the first tool that before even talking about the tools, we need to identify from where this problem can come. As we explained, we have different problems. They can come from different origins, but when you see the problem, you will see it probably at the end of your pipeline, so in your loss or a wrong prediction, but you don't know where it's coming from. And you don't know how to debug this kind of thing. So you will see a NaN value in your loss. How can I track the origin of the problem? my model is slow. How can I find the bottleneck? Is there tools to help us in these kind of things? So the first tool you have is probably the old good print. People, when they start coding, they usually bloat their code with prints and try to identify bugs. Even experienced developers would still use print sometimes because they are just lazy. And if you want to measure performance, you probably stick to using time package and just measuring the time your function is spending executing by instrumenting your code, which obliges you to modify your code first and can be time consuming if you really need to spot the slow function. So all these methods are archaic, inefficient, time-consuming, and you may spend hours or days tracking your issue. The first modern tool you have is your IDE, where like VS Code or PyCharm, if you're using PyCharm, all these tools have integrated debugger, where you could step in your code and look at your variables, execute your code step by step, put a breakpoint, conditional breakpoint, and all this stuff to track your problem. But is this enough for machine learning? Probably not. You also have profiling. So you usually in Python, you have the need to measure how much time you spend in each method. And for that, you have multiple Python profiler. Maybe the most popular one is cprofile, which comes with Python by default, which allows you to dump statistics and traces about how much time you spend in each function in your code. So, and the kind of metric you get from this profiling are the total runtime taken by a function or your entire code, the number of time each function is called, the cumulative time for each function, probably the maximum also time you spend on each call for that function, and so on. So the statistics you can get from this tool are really detailed and can go very deep. But the problem with the profiler, the Python profiler, is it will not show you the time you spent on your neural net in details, because even though you're using TensorFlow, which is a Python library, the backend code that runs the neural network and run it on GPUs is most of the time in C++ or CUDA, and the Python profiler see all that stuff as a black box. But if you want to profile your code with cprofile, it can be a start for your debugging journey, and you can easily use the profile by just running Python -m cprofile, then providing the output file profile trace, and then passing the Python code and the entry to your Python code. At the end, you will get the profile trace file, and then what you do with that profile trace. The easiest way to analyze this profile trace is to use a tool called SnakeViz that you could install easily using pip install SnakeViz. And this, by providing the file you got from the previous step to SnakeViz, you would get a nice graphic where you see the time you spent on each function here, with a nice visualization like this one in Sunflower, or something more traditional like this. So by using SnakeViz, you can quickly and visually spot where you lose time in your pipeline and training pipeline. We will see at the end of the presentation a detailed example live. So once you exhausted your analysis with traditional debugging and profiling tool, then you would ask yourself how we could do debugging and problem tracking on the machine learning side itself. The best tool on the market right now is Tensorboard, which is an open source tool that comes with TensorFlow. It can even be used with PyTorch. So Tensorboard provides measurement and visualization for machine learning workflow. So you could track metrics like loss, accuracy, or even your custom metrics. You can see the architecture of your neural network. You could project an embedding layer. For example, in your machine learning model, you would have a layer that learns a word embedding, and you want to project this multi-dimensional space in something that you could grasp visually in an easier manner. And a lot of other tools like profiling and even a TensorFlow debugger. So the profiler was introduced in Tensorboard and TensorFlow from version 2.2. So if you are using older versions, you won't be able to leverage the profiler. So you really need to use at least TensorFlow 2.2. Also, yesterday, TensorFlow 2.4 was released, and they introduced even new stuff in profiling and in Tensorboard, especially the time series section that you could discover in Tensorboard. So the first feature that you could leverage in Tensorboard is visualizing the neural network graph. So you would see a section and once you launch Tensorboard where you can see each block from your neural network, each layer, and even see where it sits. Is it running on CPU? Is it running on GPU? And you can guess this from the colors you see in the graph here. So to launch Tensorboard, you have two options. One of them is to launch Tensorboard from your command line from a console, or you could even embed Tensorboard inside your Jupyter Notebook or Google Colab if you're using it online. To activate Tensorboard on Google Colab or Jupyter, you just have to install TensorFlow, of course, but also to execute this magic command on your notebook to load the Tensorboard extension, and then you would load the Tensorboard widget inside your notebook with this command by providing the folder where you will dump the results of and your traces. A typical way to instrument and to generate statistics for Tensorboard is to use Tensorboard callback here, like in this small code snippet. So the callback will be called asynchronously by keras model fit, and it will store the information about your loss, your accuracy, the profiling inside the directory you created here. The second use case where you could leverage Tensorboard is tracking the accuracy and loss. And this is what most people use in Tensorboard. So you would, if you are using a classic or built-in training loop inside keras, you would usually get the accuracy and the loss automatically in Tensorboard. If you are using custom training loops, like here, you have to write a bit more code. And for that, you would rely on TF keras metrics, where you provide the metrics you want to track, here, the training loss, for example, or the accuracy here. And then you feed these training loss or accuracy results in this scalar, in this function TF summary scalar, and the result will be dumped by the TensorFlow summary writer, and the Tensorboard will be able to show the results in curves like here. So the final result would appear like this. You would have multiple graphs that would show you loss, accuracy, and so on. You could even, if you have too many metrics, you could filter the results from here. You could even use regular expressions to, if you have, I don't know, 100 different accuracies or metrics. So as you see, the tool is quite powerful in terms of visualization. You can smooth the curves. You can change the way you display your curves by using steps or time, relative time, in terms of training and so on. Another underused feature in Tensorboard is the possibility to inspect your image data. As we said earlier, sometimes the problem comes from bad data set, and you want to track how your data looks inside the pre-processing pipeline. For example, if you do data augmentation, you want to check that your data augmentation is correct, and what you feed to the neural network works as expected. What you could do is to dump this kind of visualization inside Tensorboard, the same way you would put scalar. And then you could spot, for example, a weird image passed to your neural network that would explain, for example, why your model is not learning. For that, you just, the same way you dump scalars, you use a file writer and a TF summary image to plot the image every, for example, end of epoch. But you need to pay attention to avoid bloating your disk or slowing down your training by dumping too much images. So you just sample some of them randomly at each epoch, for example, just to check that everything is right. You could also leverage the image capability inside Tensorboard by just plotting confusion matrix, where you could track evolution of your complex accuracy on a multi-categorical classification like this over time. And as you can see, you could have the confusion matrix every few steps during the training, and scroll here over the training to see how it evolves. Another cool feature inside Tensorboard is the embedding projector. So this allows you to, for example, you have a layer where you learn an embedding with the dimension of 500. It's complicated to understand what's happening with a vector representation of that size. So you want to, for example, use TSNE to display to project your 500 dimension vector in 3 dimension and see if you have obvious clustering or something like that inside your data, inside your embedding. And for that, you could use a projector and display it directly in Tensorboard. So, and maybe the most impressive feature inside Tensorboard is Tensorflow Profiler. Before that, if you have bottlenecks in your machine learning model, you would spend days probably scratching your heads where my problem is coming from, analyzing your pipeline, probably isolating your system piece by piece, and trying to do kind of unit test on each block and so on, which can be time consuming. With TensorFlow Profiler, you could easily visualize what's happening with your GPU and CPU, where you're losing time. You could analyze your input pipeline. You can display stats around TensorFlow. You have a trace viewer. You can profile the memory usage and so on. If you have a distributed model, you can see how your model is used over multiple pods. And maybe the most impressive feature of all and around the profiler is that you would get automatically recommendation on how you improve your model, as we will see a bit later. So in the first page of the profiler, you will get this overview page where you get first a time step graph, where you have decomposition of the time spent on each kind of task in your training, either compilation, output, input, kernel launch, host compute, device compute, copy from the CPU to GPU, and so on. And you have this section that recommends you things to optimize in your model. For example, here it tells you you're not input bound, so you don't have a problem in your input pipeline. You're not losing time loading your data. So this is what you would aim for if you want an optimized machine learning model. But most of the time when you start, you will get 95% of your time spent on input pipeline. Why is that bad? Because GPU are quite strange piece of hardware. They are fast at some kind of task, like doing convolution, doing backpropagation, and so on. But the copy of data to these devices is expensive, and GPUs do not like being starved from data. So if you are not able to feed them in a fast way the data they are processing, they will sit idle, and at the end your training will be very slow. So the first objective when you build your machine learning model is to make sure that your GPU are not starved from data. And we will see a detailed example about that. The other sections you have in the profiler are the input pipeline analysis, where you could see in details what's happening with your input pipeline. You could see here even a recommendation on how to have better input pipelines. You also have a section that would show you TensorFlow Stats, and you could see what is the time or the number of operation executed on the GPU and what is executed on the host. So when we talk, you see here on device, it means on GPU if you have a GPU. And on host, it's what is executed on the main CPU. So you usually try to put as much operation on the device as possible. Sometimes it's not possible, but you will try to write your model and your pipeline in a way where you put everything on the GPU. For example, the data augmentation on the images. If you use the appropriate implementation, you could do it on the GPU if you have enough memory, and so on. Another section that you have in the profiler is the trace viewer, where you could see here where do you spend time. You have operations here on GPU, here on GPU, and here the operations happening on CPU, and you can see the split between them. And you have also another section that would show you the GPU kernel stats. So now that you've seen the basics of profiling a machine learning model, we will try to see a practical example on how to apply all this in real life. And for that, we will use a dataset that you can find in Kaggle. It's X-ray chest images. So you have 5,000 chest images in the training set, split between normal X-ray images and images that have pneumonia. And we will not try to tune the neural network. We will just try to see how to start from a naive implementation of the data pipeline and how to spot the problems, and then how we could, through the profiler, get better performance. You can find the code that I will use in this short tutorial under my GitHub here. So in this TF profiling tutorial, so you can find all the code, and you also find a link to the presentation I've shown you today. So let's get to the practice. So we will start with this code. I'll explain quickly what's happening with this code. So this is our first attempt to load to train our model. Our data is sitting here. So we have train, we have a folder full of images here, JPEG images, quite big images, in fact, 2000 pixel by 1000 pixel at least for each image. And we have a folder with normal X-ray images and another one with images with pneumonia. So, and we want to learn to classify. So it's binary classification. So I increase a bit my screen. So what we will do is first define the folders, define the batch size, the input image that we will pass to our model. So we will rescale the image quite aggressively here, which is not necessarily good for our model accuracy. We won't do really complex image augmentation for the moment. We will do only this pre-processing task, which is rescaling the image by dividing the pixels by 255. So this function from Keras allow us to automatically process the folders. We don't have to write the plumbing code that will go through each folder and detect the class and so on. So it will do it automatically, but it expects one folder per class. Then we create a TF dataset from that by normalizing the data and extracting the features, which is the image and the labels. We do the same for the validation, but we use a smaller batch size. And then we have a simplistic neural network where we have convolutions, 2D convolutions, followed by max pooling, where we increase the size of the convolution layer until we flatten it. And then we have a dropout layer, which is a bit quite aggressive with 50% dropout. And at the end, we have dense layer, and we will do binary classification. So we will have this one here. And then we will just show the model summary. We have a learning rate. We define the optimizer. We will use binary cross entropy, and we will track the accuracy metrics. And after all this, we will do a model fit, which will train our model for 10 epochs. Now we will run this with the profiler. So as you can see, our model will is starting to train. And in order to not lose time, I'll show you the expected result. So I'll display the profiling result here. So when you launch SnakeViz, you will see something like this, where you can control how deep you will go in your profiling. And as you can see here, we see just the fit function, and we don't see that much detail, even if we go to 10. So you see really weird calls, and you don't see exactly what's executing in your machine learning model. So most of the time is spent in the PyFit here, but you don't know what's happening. You can also change the display to something like this, where you have a more global view of your problem. So basically, what the profiler says here is that we spent all our time in fit, but in fact, fit comprises the training, loading the data, so we don't know exactly what's happening with our model. So we can't get conclusion from a simple Python profiler. So for that, we will go to the next example, where we will profile the same model, but we will add Tensorboard profiling instead. So for that, we have exactly the same code. We load the data the same way, the same model. The only difference is now we are adding this callback, where we are saying to our training that we need to capture profiles from step 100 to 250, for example. And then we will get Tensorboard results. If we go back to our previous example, it's still training. So we would launch it the same way as here, but this time we won't we won't put this minus C profile here and the minus O. We just run our model regularly. And we will get the results under logs here. And you would see traces like this from Tensorboard, from TensorFlow, sorry, that would be used by Tensorboard. So to launch Tensorboard, you just you just have to run Tensorboard like this and provide the folder where you dumped your logs. So you can run it after having trained your model. So you will see this URL, which is local URL. You click on it and you get to Tensorboard. So the first screen you will see will have these curves for accuracy and loss, also epoch accuracy and epoch loss, and so on. You can have multiple training here that would appear in different folders. You can see the architecture of your graph for whatever model you are running. So you can zoom in here. The neural network itself is in this block. So if you click this plus sign, you would see your network and more details. And you see the operations and the architecture of your neural network. You see we have conv2d, max pooling, and so on. And you see the flow of data over your neural network. You can also have per device colors. You have a lot of options here that you can play with. So we don't, in this example, we don't have images, but if you have images that you want to display inside Tensorboard, if you use TF summary image, you would see them in this section in images. But here we are more interested by the profiler. So as you can see in our naive implementation that I ran a bit before the presentation, Tensorboard tells us that we have a program that is highly input bound, and we are spending 88% of our total waiting for input. Therefore, we should focus on reducing the time of input. We can go in details here to look at our input pipeline. So you see here the pink zone is the input, where we spend most of the time. And the breakdown, we are just spending most of the time doing data processing. And the cool thing is here you get some advices on how you could improve your data pipeline. As you've seen, we are just loading data. We are not doing prefetch or interleave or whatever thing. So we will see how we can quickly improve our model. So our second tentative is to try to improve our input pipeline. And for that, as we've seen that we are losing a lot of time loading our data because we are processing image by image, and Python is mostly mono thread ecosystem. So we need to find a way to parallelize the loading of the images. And TensorFlow provides a cool way to do that, is through this prefetch and caching. So by just adding cache to train to our dataset and using prefetch, you could define the buffer size manually, but you could just rely on TensorFlow to use auto-tune for the buffer size. And then you start your training the same way. So we just changed this here, and for the validation, we've done the same. Everything else is exactly the same. And if we look at the results, the overview page, just with this change, we see that now most of the compute is done on GPU because we're not losing time on the input pipeline. So this is exactly the same hardware. Here we're spending sometimes 2000 milliseconds per step. On average, we are around 200 milliseconds. And just with this change, like we are around 25 milliseconds per step and like you see that the training is quite stable over time, and we are spending 0.9% of our time processing input. Most of the time is spent processing, training the model. And you've seen how we leveraged the profiler easily to improve our model. We can see the kernel stat here. Where do we spend time in the processing? We can see the memory profile. So you see I'm not using that much of my GPU. So the green one is free. And I could also look at Tensorflow Stats, where things are executed here. So you see on CPU, most of the time is spent copying data here to the GPU. And for the GPU, most of the time is spent on the backpropagation of the convolution. And we can see here the trace viewer. You see here, this is quite good profiling. You see our GPU is always full. If you look at the other one, you can see that our GPU spends a lot of time waiting. So the empty zones are just CPU cycles where the GPU is just sitting doing nothing, because the CPU is overwhelmed here. So to come back to our presentation, so I've shown you one way to optimize your training and how we found where we are losing time using the profiler, but you have other ways that you could leverage on top of what of the TF data trick to improve your model. You could use XLA, which stands for Accelerated Linear Algebra, to improve your model. It's just few lines of code to add to your TensorFlow code. If you are using custom training loop, you could use TF function decorator to accelerate the training. Also, if you want to increase the size of your batches and you have limited memory in your GPU, you could use mixed precision, which help you have bigger batches. And finally, if you have multiple GPU sitting in multiple machines or multiple GPU in the same machine, you can use TF distribute that help you scale your model to multiple GPUs. If you want to learn more about Tensorboard, or how to optimize performance of your models, I suggest you to check these links. And finally, one last thing I forgot to talk about is Tensorboard Dev, which is a Tensorboard that is hosted on the cloud, where you could send your curves on the fly and share it with your friends or your colleagues if you are working on open source projects, of course. So your model can directly, if you are, for example, running your model on GCP and you want to share your Tensorboard curves with a friend, you could use Tensorboard Dev and I think you can store 10 million data points, if I'm not wrong. And it's quite easy to use, like this. So thank you for your attention, and if you have questions, I'm happy to answer. So, do you have any other question? Something that you didn't understand, I could explain. So thank you very much for your attention. If you have any question about how to optimize your model, feel free to contact me, and I'm available on Twitter. So Selim posted my Twitter thread. Also, maybe I'll put my personal email here. 1 second. So if you have any question about TensorFlow optimizing and profiling, you're welcome. And thank you. And see you soon.